This is a video demonstration of our initial calculations for capability studies. The introductory video on capability studies basically laid out the idea that what we're studying in this family of studies is to go in and basically check and see how well does our process meet our expectations, all right? And so we can start to do that. We can rely on a lot of familiar terms and tools that we've seen. But this is kind of our initial way of starting to look at what is going on in terms of what we're doing and does it meet our expectations. To do this, I'm going to look at a problem from one of our white papers for BA 254 related to capability studies. The first problem starts off by saying the process, or given a process in statistical control with a normally distributed population. Now, this is an important disclaimer. What this says is we've basically gone out, we've improved the process as best we can. Because one of the dangers is, of course, just like anything else in life, if you've just tried it a few times and you haven't really studied it, you can't say that that's the very best that you are capable of. All right. So what this says is basically we've studied it through a number of different ways. If you look at business operations, there's a whole field related to design of experiments that would say we don't know anything about the process and we're early stages of setting it up. We would have conducted that work, okay? This problem assumes that that work has been done, all right? It goes on and says the process has an upper specification limit of 40 and a lower specification limit of 30. Sample of 32 yielded an X bar of 36 and a standard deviation of 3.45. So just like we've come to, it's kind of become our habit, we're going to write out the given information first. We're going to write that down. My upper specification limit equals 40. My lower specification limit is equal to 30. It says we went in and we conducted a sample of 32. We resulted in an X bar equal to 36 and a standard deviation of 3.45, right? Calculations that we're familiar with, right? This location and dispersion measures. First part of this problem then is we're going to go in and calculate what's called the overall process capability. We're going to calculate the CP. We're going to do that with this formula, the upper specification limit minus the lower specification limit, all divided by 6 times our standard deviation. All right, simple formula. Basically what we're doing in this first step is we're going in and saying, all right, I've got some process. It looks like that. We're basically saying if this is my lower specification limit and this is my upper specification limit, irrespective of where it's located, we're going to calculate a number that basically kind of says, the question is how well do 6 standard deviations fit in there? That's our standard that we're looking to meet in this calculation. So my upper specification limit was 40 minus my lower specification limit of 30 divided by 6 times 3.45. I calculate that number out. I end up at 0.48, we'll call it 3. That is my overall process capability, all right? Now, the higher bar, what we're going to do next is we're in part B here, going to then calculate the CPK. To calculate this CPK, it's going to equal the minimum of 2 values, a CPL and a CPU, okay? To calculate this CPL, we're basically going to go in and we're going to take our X bar minus our lower specification limit, all divided by 3 times the standard deviation, all right? When we calculate the CPU value is going to be my upper specification limit minus my X bar, all times, or divided by 3 times my standard deviation, okay? So now, instead of just looking at the overall process and how it fits, we're taking and breaking the distribution kind of down by saying what is the relative position of those values, and now we're evaluating still over an aggregate of 6 standard deviations, but we're taking them 3 at a time. In terms of calculating this value, we're just going to put our numbers in here. We had an X bar equal to 36 minus 30 is my lower specification limit, all divided by 3 times 3.45. That results in a CPL of 0.5, we'll go 80, round that slightly. And my CPU is then my upper specification limit was my 40 minus my 36 divided by 3 times 3.45. If I calculate that CPU value, it ends up being, we'll go 0.387. Okay, 0.387. The minimum of these two values is this 0.387. All right, that's not good. We can then start to apply that or look at our rules that we talked about in the introductory section on capability studies. And those rules, if you remember, basically said, we have a capable process if this CPK value, the CPK value is greater than 1.33. That's our current standard. We can talk about when those standards would be different later. We're talking about medical studies and aircraft manufacture and automotive manufacture and some very specific areas where we might have a bit of a different standard. But in this case, our standard is as long as our CPK value is greater than 1.33, we're in the clear. We said, yes, it's capable with tight controls if it's between 1 and 1.33. Again, clearly not. So we're left with kind of this last scenario, whether it's capable or not, which is ultimately the question we're asking. And we're going to say no. Why? Because the CPK value is less than 1. All right. In the next video, I'm going to discuss how we can calculate an expected parts per million, which will be another way to kind of explain this condition and the fact that it's representing a real limitation on what we can do. But in terms of the general calculation of these CPK and CP values, they're very straightforward. We're just basically finding the formulas, plugging in our numbers, and then using our established evaluation criterion to figure out what those represent.